In 1940, in the wartime, Great Britain was fighting with its backs against the wall. All the aeroplane manufacturers were struggling with orders, so overseas sources had to be looked at. The British Purchasing Company, the BPC, had an office in New York. An order was placed for Curtiss for their P-40 design. In England, we call that a Kitty Hawk.
What if the future of private aviation looked less like a jet and more like a flying egg? Otto Aviation spent years developing the bizarre Otto Celera 500L.
The Otto Celera 500L. And it packs some truly amazing performance figures. Or how about this? Picture this aircraft flying with a range of 4,500 nautical miles.
An aircraft designed around one obsession: cutting drag to levels conventional planes could never achieve. Its strange fuselage, rear-mounted diesel V12, massive cabin, and incredible fuel efficiency claims made it look almost too good to be true. But this wasn't just a computer concept. The Celera actually flew dozens of test flights. Then everything changed. Otto abandoned the production version and revealed an entirely new jet using the same aerodynamic technology. So why kill the aircraft that proved the idea? Let's find out. The strange plane begins here. So where does an aircraft this strange actually come from? It started with a small American startup called Otto Aviation, founded back in 2008 by a man named Bill Otto Sr. And Otto wasn't some weekend hobbyist tinkering in a garage. He was a former research scientist at Los Alamos National Laboratory, later a systems engineer, and eventually chief scientist at North American Aviation, the same company behind the P-51 Mustang fighter of World War II and the X-15 rocket plane that once flew to the edge of space. Otto's question when he started the company was almost embarrassingly simple and brutally hard to answer. What would an airplane look like if you designed it from scratch, with zero compromise, purely to minimize drag? Not a tweaked version of something already flying. Not an evolution of a familiar Cessna shape. A completely clean sheet, with one single obsession guiding every decision. Otto and a small team locked themselves away and went to work, starting construction in 2015. It took 3 years, and in January of 2018, the prototype took off for the first time. The test pilot for that maiden flight was a man named Bjarne Tryggvason, a former Canadian Space Agency astronaut who had actually flown aboard the Space Shuttle Discovery back in 1997. Otto wanted someone with serious test flight discipline running the program, and Tryggvason brought exactly that kind of scientific rigor to every single data point the aircraft produced. For years after that first flight, almost nobody outside the small team in Yorba Linda knew this aircraft existed. Otto Aviation stayed privately funded and deliberately quiet, flying test after test away from public attention, refining the design based on real flight data rather than rushing to a press event. That kind of patience is unusual in an industry where startups typically want headlines as early as possible to attract the next round of investment. Otto seemed to prioritize getting the physics right first and let the announcement come later, once there was real flight data to back it up, rather than just a rendering and a promise. Building the thing was its own kind of battle. A small team working out of a single hangar doesn't have the resources of a major aerospace manufacturer. No army of subcontractors. No existing tooling built for this shape. Every mold, every jig, every fixture needed to produce a fuselage, this smooth, had to be designed essentially from scratch, because nothing like it existed on any factory floor. That's part of why the timeline stretched to 3 full years, just to get from the start of construction to a first flight, an eternity by the standards of a well-funded major manufacturer, but a remarkably fast pace for a handful of engineers building an entirely new kind of airframe by hand. So what does the finished aircraft actually look like? It looks, frankly, a little ridiculous, like an egg with wings, or a submarine that took a very wrong turn. There's a reason for that, and it's not an accident. The fuselage stretches about 41 feet long, roughly 12.5 meters, shaped like a teardrop or a bullet, or if you squint hard enough, a small zeppelin. The wingspan runs 52 feet, about 15 meters, absurdly long and narrow, closer to the wings you'd see on a competition sailplane than anything you'd expect on a business aircraft. And the propeller sits at the back in what's called a pusher configuration, rather than pulling the plane through the air from the front. It helps to understand just how unusual Otto's background made this project possible in the first place. Most aircraft manufacturers start from an existing airframe and refine it generation after generation, chasing incremental improvements. Otto approached the problem the way a research scientist approaches an open question, stripping away every assumption about what an airplane is supposed to look like and starting purely from the physics. That's an almost unheard of luxury in aviation, where certification pressure and manufacturing cost usually force compromises long before an engineer gets to chase pure aerodynamic theory this far. Every single curve on this aircraft, every panel, every rivet placement or deliberate absence of one exists for a single purpose, keeping the air flowing over the surface, doing one very specific thing: staying smooth, staying orderly, staying what aerodynamicists call laminar. And that word laminar is really the whole story here, so it's worth actually understanding what it means before we go any further. The secret behind the Celera. Laminar flow is in a lot of ways the holy grail of aerodynamics, and almost no aircraft in regular service actually achieves very much of it. Here's an easy way to picture it. Imagine pouring honey down a perfectly smooth sheet of glass. It flows in clean, parallel sheets, one thin layer sliding past the next without any mixing, no swirling, no turbulence. That's laminar flow. Smooth, orderly, predictable air hugging the surface it's flowing over. Now imagine pouring that same honey down a rough concrete surface covered in bumps and ridges. The honey breaks up almost instantly. It starts swirling, tumbling, tangling with itself. That's turbulent flow, and that's essentially what happens to the air moving over almost every airplane currently in service. Rivets, panel seams, antennas, lights, drainage holes, every one of those tiny features trips the airflow from smooth to turbulent within the first few feet of the nose. And turbulent flow is exactly what creates drag. Not a small amount of drag either, a massive amount, and drag is what burns fuel. Otto's entire design philosophy revolves around eliminating that turbulence at the source. No exposed rivets, smooth panel joints, no unnecessary protrusion anywhere on the airframe. The result, according to Otto and corroborated by multiple aviation publications who've covered the aircraft, is a 59% reduction in drag compared to a similarly sized traditional aircraft. 59%. Picture cutting the air resistance on your car by more than half. It's worth explaining why almost no other aircraft manages this. Manufacturing an airplane skin smooth enough to sustain laminar flow.
The manufacturers behind the Stratolaunch, the world's largest all-composite aircraft, used hypersizer software from Collier Research to automate design, stress analysis, and sizing optimization.
Requires an almost obsessive level of precision, tolerances measured in fractions of a millimeter across an entire fuselage, because a single proud rivet head or a slightly misaligned panel seam is enough to trip the airflow back into turbulence. Most manufacturers simply accept that trade-off, because building to that level of precision at scale is expensive and slow. Otto's entire business case rests on proving that precision is worth the cost, because of how much fuel and weight it ultimately saves. There's a nice bit of historical irony buried in this story too. That P-51 Mustang Bill Otto's old employer helped build was actually one of the very first production aircraft to attempt a laminar flow wing design, back in the 1940s. The wartime manufacturing tolerances of that era simply couldn't hold the precision needed to sustain true laminar flow in practice, so the concept mostly stayed theoretical for decades. Otto, having come up through that same aerospace lineage, essentially spent a career chasing the promise that a generation of engineers couldn't quite deliver on, until modern manufacturing finally caught up to physics. It's worth pausing here for a moment of honesty, though, because not everyone in the aviation engineering world is fully convinced that numbers hold up perfectly in every real-world condition. The Royal Aeronautical Society, a respected professional body in the field, has publicly noted that achieving the full 59% figure would be a genuinely difficult task, and pointed out that lift-induced drag specifically isn't something laminar flow alone can reduce. That's a fair technical caveat, and it doesn't erase what Otto's flight tests actually recorded, but it's the kind of skepticism worth knowing about before you take any single number as gospel. To understand that caveat a little better, it helps to know that drag on an aircraft actually comes from more than one source. There's skin friction drag, caused by air rubbing against the surface of the aircraft, which is exactly what laminar flow is designed to reduce. But there's also lift-induced drag, a separate force that comes from the very act of generating lift in the first place, tied more to wing shape and aspect ratio than to surface smoothness. Otto's long, narrow sailplane-style wings help address that second category too. But the point critics raise is a fair one. Laminar flow alone, no matter how perfectly executed, can only ever address part of the total drag equation, not all of it. So that's the theory, and that's the honest pushback against it. But theory only matters if it actually translates into a real, flyable machine. And that's where the engine and the raw performance numbers come in. The diesel engine nobody expected. Here's the part that tends to break most aviation people's brains a little. The Celera is powered by a single engine at the back, driving that pusher propeller, and the engine itself is called the Red AO3, built by a German company called Red Aircraft. It's a V12, twin-turbocharged, liquid-cooled design.
This is a 2,000 horsepower quad-turbo V12 that makes every electric supercar look incredibly boring. This is going to be a cool one. Me and Tombo are in Turin.
Producing somewhere around 500 to 600 horsepower. And here's the twist. It's a diesel engine, not a gas turbine, not a turboprop, not a typical aviation piston engine running on high-octane fuel. A diesel cycle engine, capable of running on standard Jet A1 fuel, biodiesel, or sustainable aviation fuel. Otto has actually flown complete test flights entirely on sustainable aviation fuel, and the engine has been fully certified both in Europe and by the FAA, which is genuinely one of the rarest achievements in aviation. A radical engine concept that's already certified is almost unheard of. That multi-fuel flexibility matters more than it might sound. An owner isn't locked into one specific fuel supply chain the way most turbine-powered aircraft effectively are. Sustainable aviation fuel can be produced from used cooking oil, agricultural waste, or other non-petroleum sources, and because the Red engine runs on it without any hardware modification, the same pump, the same injectors, the same operating parameters, an operator could gradually shift toward greener fuel sources as they become more available in a given region, without ever needing to retrofit the aircraft itself. That kind of built-in adaptability is rare in aviation, where engines are typically certified for a narrow, specific fuel spec and stay locked to it for their entire service life. So why choose diesel at all? Diesel engines are, generally speaking, more thermally efficient than typical aviation gasoline engines, and pairing that efficiency with a turbocharger that maintains power at high altitude gives you a power plant with both strong fuel economy and multi-fuel flexibility. There's also a maintenance argument in diesel's favor that doesn't get talked about as often as the fuel numbers. Diesel cycle engines generally run at lower peak temperatures than turbine engines and tend to go longer between major overhauls, which, if it holds up over the aircraft's service life, would mean fewer expensive maintenance events and less downtime for an owner over the years. Otto's projected fuel economy for the Celera sits somewhere between 18 and 25 nautical miles per gallon, with some reports citing figures closer to 30 at optimum cruise. For comparison, a typical mid-size private jet, carrying the same number of passengers on the same trip, burns somewhere around 2 to 3 nautical miles per gallon. That's the gap that lets Otto claim the Celera uses roughly a sixth to an eighth as much fuel as a comparable jet. Now, shape and engine mean nothing if you can't actually fit people inside comfortably, and this is where the Celera does something genuinely strange for an aircraft this aerodynamically extreme. Before we get there, it's worth understanding why the drag reduction pays off so much more than it might first appear. Less drag means the engine doesn't have to work as hard, which means it can be smaller. A smaller engine burns less fuel, which means smaller fuel tanks are needed to hit the same range.
There was flight test data on the aircraft that showed incredible fuel burn, incredibly low fuel burn, and the laminar flow performance.
And that data was used to help refine all of our technology and tools to build the second aircraft, which is now called the Phantom.
Which means less structural weight to carry that fuel. Which means the wings and landing gear can be lighter too, since there's less weight to support. Each improvement makes the next one easier, a kind of compounding effect that engineers sometimes call a virtuous cycle. That's part of why a 59% drag reduction doesn't just translate into 59% less fuel burn, it cascades into savings across nearly every system on the aircraft. Low drag shapes are usually thin, cramped, built more like a fighter jet or a glider cockpit than a cabin you'd want to sit in for hours. But the Celera somehow pairs its low drag fuselage with a surprisingly massive interior. The cabin ceiling sits at about 6 feet 2 inches, roughly 1.9 meters, tall enough to stand up in fully. 6 first-class style passenger seats, a lavatory, and a cabin volume Otto quotes at around 448 cubic feet. For comparison, a Beechcraft King Air 350 offers around 416 cubic feet, and a Cessna Citation CJ3 Plus,
the gorgeous Cessna Citation CJ3. I'm working on my type rating right now, so I actually just flew this one in here, so let's take a tour of this plane.
offers only around 311. So despite looking like a torpedo from the outside, the Celera actually beats both of its closest competitors on interior space. You're not trading comfort for efficiency here. Somehow, on paper at least, you're getting both. As for raw performance, the projected cruise speed sits around 400 knots, roughly 460 miles per hour, at an altitude of 30,000 feet, with a range of about 4,500 nautical miles on a full tank, with 6 passengers aboard. And then there's the glide ratio, 22:1. 22 horizontal feet of glide for every single foot of altitude lost. Put another way, 22 miles forward for every 1 mile down. Most business jets glide at somewhere around 15:1. From a cruising altitude of 30,000 feet, the Celera could theoretically glide more than 200 kilometers, roughly 120 miles, with the engine completely off. That turns an engine-out emergency at altitude from a desperate scramble into a long, controlled descent toward the nearest airfield. All of these numbers sound almost like marketing fiction. So the obvious question is, did any of it actually happen in the real world? Or is this all still theoretical? The Celera was actually flying. This is the part of the story that separates the Celera from a lot of the ambitious concept aircraft that never leave a wind tunnel. Everything described so far wasn't just modeled on a computer. It was flown, repeatedly, and measured. The aerodynamic prototype rolled out of Otto's hangar in late 2017, with its maiden flight following in January of 2018. By August of 2020, the prototype had completed roughly 31 test flights, and Otto took the design public at a press event in Victorville, California. The aviation world's reaction was, by most accounts, a mixture of fascination and outright disbelief. By November of 2021, the count had climbed to around 55 flights and 51 cumulative hours of flight time, including, in 2024, a full test flight conducted entirely on sustainable aviation fuel. That Victorville unveiling in particular is worth understanding, because it wasn't a typical splashy aerospace reveal built around a rendering or a mock-up sitting still on a stage. Otto rolled out an aircraft that had already logged real hours in the sky, alongside actual flight test data, ready to be scrutinized by journalists and engineers on the spot. That's a very different posture than most aerospace startups take, where the marketing usually arrives years before the hardware does. It meant that from day one of public awareness, skeptics couldn't simply dismiss the Celera as a rendering with impossible promises attached to it. There was already a real airplane, with a real flight log, to argue about. Each of those flights was designed to validate a specific performance claim, not just generate headlines. The 59% drag reduction, tested and measured in actual flight rather than only in a wind tunnel. The glide ratio, tested. The fuel burn figures, tested against real flight data rather than theoretical projections. It's worth being precise here about what's independently confirmed versus what remains Otto's own internal projection. The drag reduction and basic flight performance figures have been corroborated across multiple aviation publications who reviewed Otto's flight test data directly. Figures like the exact operating cost per flying hour and specific emissions percentage reductions, however, come from Otto's own internal analysis and should be treated as the company's claim rather than an independently audited number, at least until the aircraft goes through full certification scrutiny. Laid out together, the pattern is hard to dismiss as marketing spin alone. A cruise speed near 400 knots, matched against jet-like speed claims. A range past 4,000 miles, matched against real long-distance test legs. A glide ratio near 22-to-1, matched against actual dead-stick descent testing rather than a spreadsheet calculation. Each individual number could, in isolation, be written off as an optimistic projection. But when the same aircraft keeps hitting projection after projection across dozens of separate test flights spanning several years, the more reasonable read isn't that Otto got lucky repeatedly, it's that the underlying aerodynamic theory actually works the way Bill Otto believed it would back in 2015. Still, for a technology this radical, having more than 50 real flights and over 50 hours of validated data behind it is a genuinely unusual level of proof. Most ambitious aerospace concepts never get anywhere close to that kind of real-world testing before either running out of funding or quietly disappearing. There's a broader lesson in that persistence, too. Aviation history is full of aircraft that looked incredible in a press release and a computer rendering, and then either never flew at all or quietly vanished after a handful of demonstration flights designed more for cameras than for genuine data collection. What separates the Celera from that graveyard of concept aircraft is the sheer volume of unglamorous, repetitive flight testing behind it, year after year, long after the initial press excitement had faded. That's usually the difference between an idea that stays a rendering forever and one that eventually becomes real hardware other companies are willing to bet billions of dollars on. Which makes what actually happened next even more surprising. The twist nobody saw coming. Here's the part of this story most people never hear. By the end of 2024, Otto Aviation had completed its test program. All the laminar flow claims, all the drag reduction figures, all the fuel economy projections, all validated in flight. The prototype had delivered essentially everything Bill Otto had promised back in 2015. A wind tunnel theory had become a real, flying machine. And then, in 2025, the company did something nobody expected. It pivoted entirely. Otto Aviation renamed itself Otto Aerospace, brought in a new chief executive named Paul II, and relocated its headquarters to Fort Worth, Texas. At the Paris Air Show that same year, II stood alongside Florida's governor and announced a $515 million state incentive package to build a new manufacturing campus at Cecil Field in Jacksonville. And then came the real surprise. The Celera 500L, the aircraft we've spent this entire video talking about, would never actually become a production airplane. In its place, Otto unveiled the Phantom 3500, a completely clean sheet, all-composite mid-size jet, applying the exact same laminar flow principles proven on the Celera, but now powered by twin Williams FJ44 jet engines instead of the diesel piston engine.
Hi, Rich Pickett. I'm going to talk about the Williams International FJ33-5A engine. It generates 1,846 pounds of thrust at sea level.
First flight is targeted for 2027, with FAA certification expected by 2030. And in September of 2025, FlexJet, one of the largest fractional ownership operators in the world, placed a firm order for 300 of them, a deal reportedly worth somewhere around $5 billion, one of the largest private aviation orders in recent history. Between now and that 2030 entry into service, Otto still has a considerable amount of work ahead of it. The company needs to finish detailed engineering, build several flight test vehicles in a production representative configuration, and carry the Phantom through the same kind of rigorous flight test program that validated the Celera years earlier, only this time under far more public scrutiny, with a paying customer and a firm delivery commitment already on the books. That's a very different kind of pressure than quietly testing a technology demonstrator in relative obscurity. But having already proven the core aerodynamic theory once, on a real aircraft with real flight hours logged, gives Otto a credibility foundation that most clean sheet aerospace programs simply don't get to start with. So what was the Celera actually for, if it was never going to be sold? It was a technology demonstrator, plain and simple. Its entire purpose was to prove that laminar flow could genuinely work at scale, on a real aircraft, with real manufacturing tolerances, not just inside a wind tunnel. And the flight test data proved exactly that. Every one of Bill Otto's original claims from 2015 held up under real flight testing. And those validated results are now the foundation Otto Aerospace is using to attract billions of dollars toward the Phantom. It's worth sitting with just how significant that FlexJet order actually is. Fractional ownership operators like FlexJet don't place orders of that size on speculation alone. They're betting real capital on an aircraft years before it's even certified, based largely on the credibility Otto built through the Celera's flight test record. In an industry where new aircraft programs routinely slip years behind schedule or fail to reach production at all, a firm order for 300 aircraft from an established operator is about as strong a vote of confidence as an unproven aerospace company can receive. It's the clearest sign yet that the strange-looking prototype in that California hangar did exactly what it was built to do. The egg-shaped aircraft in that California hangar didn't fail. It succeeded so completely that it convinced one of the largest fractional jet operators on the planet to place a multi-billion-dollar order for whatever comes next. In the end, the strangest part of the Celera story isn't that an egg-shaped aircraft actually flew. It's that the aircraft was never supposed to be the final product. Otto Aviation used the Celera to prove that extreme aerodynamics, laminar flow, and radically lower drag could work outside a computer simulation. More than 50 flights later, that proof became the foundation for something far bigger: the Phantom 3500, a new mid-size jet backed by a reported multi-billion-dollar order from FlexJet. But the biggest question remains: can Otto turn years of experimental success into a certified aircraft that actually changes private aviation? The Celera proved the idea. Now the Phantom has to prove the future.